Hello everyone, my name is Han and welcome to my channel. Today we take a look at our first crypto system called RSA. It's a very popular crypto system. It's one of the first public and private key crypto system and is still widely used. With the knowledge of Finite Fields that we recently acquired, we can understand how it works. So we will not be able to prove that it's safe against cryptanalysis and code breaking, but generally speaking, cryptanalysis is much beyond our scope. So the first step is key generation. So for RSA, the key generation is we choose two prime number, P and Q. So a prime number, just to remind you, is an integer greater than 0, such as it has exactly two dividers. It has 1 and it has itself. So 2 is the first prime number, because 1 is not a prime number since it only has one divider. You need 2. 2 is a prime number because it has 1 and 2 divider. And every number, every integer will have 1 in itself as a divider. So that's a given. A prime number only has these two. So the next ones will be 3, 5, 7, and 4 is not a prime number because it's 2 times 2. So therefore it has 3 dividers. It has 1, 2, and 4. So once you have these two prime numbers, and normally you would choose them to be very, very large, but for the example we're taking, we're going to take two small numbers because otherwise it would be too hard to understand. You take these two numbers and you multiply them. So n would be the product of P and Q. In our example, we will use P equals 3 and Q equals 5. So once you multiply them, you get 15. And that's going to be our little n. Now we calculate the product of P minus 1 and Q minus 1. And that's our big N. So in this case, P minus 1 is 2 and Q minus 1 is 4. So the product is 8. And that product should be kept secret. Then we choose encryption key, which is a number between between 3 and big N. So it could be any number. Here I would choose equal 3. And we find the inverse of E in the F N group. So the number D, such as D times E equal 1 modulo big N. So in our example, E equals 3, right? The big N was 8. So we need to find a number such as D times 3 is equal 1 modulo 8. We can search and we can see that number 3 works because 3 times 3 is equal 9 and 9 is 1 modulo 8. And we have our public key. So our public key is little n and E. In this case, little n is 15 and E is 3. And our secret key is little d, the inverse of E. So here actually our secret key is also 3, but that's just a coincidence. And after this, we can discard big N, P and Q. So we only keep N, E and D. So now how do we do the encryption and how do we do the decryption? So with RSA, one interesting thing is that you can either use E or D to encrypt, and you just need to use the other one to decrypt. So you can encrypt with E and decrypt with D, or you can encrypt with D and decrypt with E. So the second case is when you want to do a signature, and the first case is when you want to do a regular encryption. And you can notice that that's fairly obvious that it works because in the equation E times D equal 1, the role of E and D are interchangeable. So let's suppose that we want to do the encryption, the regular encryption. So we are going to use our E, and so we use the public key. So we use public key E and N, and we are going to use the secret key D to decrypt. So we start with the message M, and we calculate the ciphertext. So the encryption of M is called a cipher. To do the encryption, to calculate cipher C, we take M and we multiply by itself E number of times. So that's written as M power E. Of course, everything has to be done in a group and has to be done modulo N. And to do the decryption, we do exactly the same thing, but this time we use the cipher C, and we raise at the power of D, the decryption key. So we take C and we multiply by itself D times, and we should get the original message. So what I'm saying is that if we say C equal M power E, then C power D recovers M. So let's try. Let's try with a message M equal 2. We do M power 3 because the encryption E was 3. Right? We can always use equal 3 regardless of our choice of secret. So we do 2 power 3, and that's 8, which remains equal to 8 modulo 15, and is 15 in our case. So our result is C equal 8. And now to do the decryption, we do 8 power D, and in our case, it happened that D and E were the same, so we'll also raise to the power of 3. Again, that's just a coincidence. So we take 8 and we raise power of 3, so 8 times 8 times 8, and that gives us 512, so which is way beyond the modulo 15 of the modulo 15. So now we have to reduce that to an element of the between 0 and 14, and we notice that 512 is 2 plus 34 times 15. So we drop the 34 times 15, and the result is 2, which is the same as the original message. So as you can see, in this very simple example, we were able to encrypt the message by raising it to the power of E, and we were able to decrypt it by raising the cipher to the power of the decryption key. So now let's see why it works, and let's prove that it actually works regardless of the value of M. So we have to prove that if we take C and we raise it to power D, we get M again, modulo N. So C was equal to M power E, and now we have C power D. So if we combine these two equations, we are saying that the message we are calculating, so far we're not calling it M because we want to prove that the result is equal to M. So let's call that result M prime for the moment. So let's call M prime equal C power D. Right? The goal is to prove that M prime is equal to M. All right. So far we have M prime equals C power D, and we know that C is equal M power E. So that's saying that we are M power E power D. And we know that also that when we raise things to the exponent, the exponents multiply. Okay. So M power E power D is the same as M power E times D. And we still haven't proven anything, but the goal here is to prove that that is the same as M. So if we remove one M factor, so we divide basically by M, we would say that we are trying to prove that M power ED minus 1, right, is equal to 1. We basically divide by M on each side, modulo N, of course. Right? And to establish that result, we need a theorem, or we don't have to reuse this theorem, but it's actually quite easy if we use that theorem, which is called the Fermat's little theorem. And not to be mistaken with the Fermat last theorem, which is much harder. The little theorem is actually fairly simple to prove, and we are going to prove it afterwards. But what does that theorem say? It says that if you have a prime number and you have any value a in the range 0 to p minus 1, so in the normal range, if you take that value a and you raise it to p minus 1, then it's equal to 1 modulo p. So that result is going to be proven later, but for the moment, we're just going to use it and take it as granted. All right, so with that in hand, what can we do? We have m power ed, and we want to prove that it's equal to m. Right, so we subtract m, we move m on the other side. We have m power ed minus m should be equal to 0 now, modulo n. Right. So if something is equal to 0 modulo n, it means that that thing is a multiple of n. And therefore, it can be written as k times n. There's a case such as that number is equal to k times n. Right. And our n, by definition, is equal to p times q. Right? That's the definition. That's how we build. We choose n in the beginning. So now we want to prove that m power ed is equal to m modulo p and modulo q. So all we're saying here is that m power ed minus m is a multiple of both p and both q, just because it's a multiple of the product of the two. So it's very intuitive, but you can always write it out if you want to be if you're more comfortable with that. All right, so we just need to prove now that m power ed equal m modulo p, because since p and q play exactly the same role, they are symmetrical, we would also have the same result with q, just using the same proof. So how do we do that? Right. So we have two cases. If m equals 0, then we have m equals 0 modulo p, which again means that p divides m. M is a multiple of p if you prefer. Well, so if p divides m power ed, so m power ed is m multiplied by m ed times. So that's also a multiple of m. Therefore, since p divides m, p divides any multiple of that thing, right, of that m. So p also divides m power ed. So therefore, m power ed is also equal to 0 modulo p. So that's the easy case. So now we consider a case where m is not equal to 0 modulo p. In this case, then we can rewrite m power ed by just moving one term of m out. So m power ed is m power ed minus 1 times m. We just move one factor m outside. But since ed equal 1 modulo big N, by definition of our secret key, right? We had our secret key be the inverse of e modulo big N. Right. So if we have that statement, it basically means that there is a k. Again, the value of k doesn't really matter, but there's a k such as e times d is equal kn plus 1. And if you take that and you inject it into the equation before, we have m power ed minus 1 is equal to m power kn. Right. And n, big N, this time big N, is equal to p minus 1 times q minus 1, again by definition of big N. Right. So we have the result, m power k times p minus 1 times q minus 1. And we use the fact that the exponents, if you have a product of exponents, it's the same as moving the exponent out, raising up. So basically what you have, x power ab is equal to x power a and the whole thing power b. And so we can move the exponent out, and that gives m power p minus 1, the whole thing, power k times q minus 1. We basically isolated the terms p minus 1, right? And by by using the Fermat-Little theorem, which we recognize that it has a very useful property for p minus 1 when p is prime, we have the fact that m power p minus 1 is equal to 1 modulo p. So now what happens is that the term m power p minus 1 is actually equal to 1. And we're simply multiplying 1 by 1 k times q minus 1 times. So the whole thing is basically equal to 1 because you're just multiplying 1 by 1. And 1 is a neutral element. You can multiply it as many times as you want. It's still going to be 1. Right? So the end result is that m power ed minus 1 is equal to 1, of course, modulo p. And you have that m power ed is equal to m. Right? Because m power ed is equal to m modulo p. We use the same reasoning and we have m power ed is equal to m modulo q. Therefore, m power ed modulo is equal to m modulo pq, which is the same as m power ed is equal to m modulo n equal pq. And therefore, you have the result that m prime is equal to m. So that was, hopefully, I hope that it was not very complicated. Right? We just use very simple properties of multiplications and the stuff that we know about how they combine in exponents, and we got to the result that the decryption works the same way as encryption, just by using the other key. So either the secret key if you're using the public key, or the public key if you were using a secret key to encrypt. So now the rest would be about proving more and more things, and you can skip it if you're not super interested with the details. But for completeness, I will give the proof of the Fermat-Little theorem, so that we are not using anything that we haven't seen earlier. So how do we prove Fermat-Little theorem with the things that we have seen? So we know that in a discussion about finite fields, we saw that Fp is a field if p is a prime number. And the definition of the field is that Fp star is multiplicative from a group. So Fp star is again the elements of Fp, which are elements 0 to p minus 1. But Fp star is this without the 0 element. So 1, 2, 3, 4, and again all the way to p minus 1. They must form a group for the multiplicative law. And the tricky part here is that we need to prove that if p is prime, every element of that set has a multiplicative inverse. And we left it an open question. We just said it was not trivial, and we are going to also prove it a bit later. But that's also a bit more complex. So for the moment, we will also assume that we have that result, and that we know every element of Fp star has an inverse. So now, if we take the set made by multiplying 1 by a being any number, so we have 1, a square, a cube, a power 4, and we keep multiplying by the previous element by a until we loop around. And we know we're going to loop around, we're going to go back to 1 because the number of elements in this set is not infinite. So you're going to end up having to reuse an element that you have used before. And when it happens, we close the loop. Basically, we have formed a subgroup, and that lowest element we call it k. So by definition, k would be the element such as a power k is equal 1. So you will have the element 1 a squared dot 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 all the way to a minus k minus 1. And the next one would be a minus k, but we know it's equal 1, so we have already that element. Therefore, the number of elements that you have in this group is k. And we know that if you have a subgroup of a group, its number of elements must be a divider of the number of elements in the group. So if we take the example of minutes of clock, and we know that we have this time it's an additive group, but it's the same applies to a multiplicative group. You have 60 minutes. So if you do a minute plus 1 minute, after incrementing by 60, you have wrapped around. You went back to 0. And you also know that if you instead of incrementing by 1, you increment by 5, right? Or by 10. Let's go by 10. You would go 10, 20, 30, 40, 50, and then you go back to 0. So now you have you loop around, and you see that 10 is a divider of 60. But if you, instead of just doing 6 steps, after 6 steps you went around, if you still do 60 steps, you're still going to do get back to 0. It's going to be just, instead of having done 1 hour, you made 10 hours. But the result modulo hour is still going to be 0. So this works every time you do an even number of steps, you go back to the beginning. So this is kind of hand waving, but the formal proof is will work relatively easily too. That every subgroup, every cardinality of every subgroup should be a divider of the cardinality of the main group. So what we are saying here, if we apply this result here, is that k is a divider of p minus 1. There are exactly p minus 1 elements in the fp star. So once we have that, we know that if we do a times p minus 1, you are basically going to do a times k, and then do it again a certain number of times. But at that moment, you're going to be basically multiplying 1, right? Because you already have done a loop. And then the result would be still 1, because 1 is a neutral element for the multiplication. You can multiply 1 by itself any number of times you want, it's still going to be 1. So at the end, you have the result that a power p minus 1 is equal to 1 modulo p, which is the Fermat-Little theorem. So if you want to continue down the rabbit hole, you may ask, why is fp star a multiplicative group, right? Because once we have that, it's the proof of Fermat-Little theorem was rather simple. But then the question is, okay, we use that result, and we should prove that result as well. Okay, so we can do that by using a lemma. And again, it seems like we are introducing more and more stuff. And we have to also prove the lemma, the Bezout's lemma that we are going to use. But for the moment, again, let's assume that this lemma is already proven, is given to us. And this lemma, Bezout's lemma, is that if you have two integers, and you calculate their greatest common divisor, we call it D. So you have two integers, and their greatest common divider. The lemma says that there are two numbers x and y which are integers, but this time these integers can be either positive or negative or even 0. And these numbers are x and y, such as a times x plus b times y is equal to d. So this nice symmetrical equation, which basically says that you scale a and you scale b, and once you add the two together, you will get the common divider and the greatest common divider. Okay, so how do we prove this lemma? This lemma, the proof of this lemma is actually quite interesting because it's a technique that is actually used quite often in algebra to solve these many problems. So what it does is that you create a set that by construction is not empty, and that is positive, that all the elements of that set are positive. And a set like that has the smallest element. This is pretty intuitive. It means that if you have a set of numbers, there's a smallest element to that set. And then you pick up that smallest element, and then you prove that you calculate something that you are going to find is also an element of that set. And since that element cannot be and is lower than the smallest, then it cannot be. You get it to a contradiction, right? So let's do that trick here, right? We create a set of all the numbers that are of the form ax plus by, right? So you take any combination of linear combination of a and b, and you're only interested in the ones that are positive, right? So, but this set is clearly not empty because a and b are in the set. If a and b are positive, if a is negative, you just swap it. You do minus a is going to be in the set. So that set is not empty, and therefore it has the smallest element. So we take that smallest element and we call it d, right? And now we want to prove that this element, it turns out to be the greatest common divider of a and b. All right. So how do we do that, right? We take that element d, and so far we don't know that it's the greatest common divider, but we know that that element is the smallest element of the set that we have defined. And we use the integer division. So it's called the Euclidean division. So it's a standard integer division, which says that if you have two numbers, you can divide one number by the other, and you will have a quotient, and you will have a remainder. And the remainder will be positive, but below lower than the number you're dividing by. So if you want to divide a by d, you're gonna have a equal d times q the quotient, plus r, where r is greater than 0, greater or equal to 0, but strictly lower than q. So once you have that, you just move, you factor r, so you move dq to the left side, and you say that r is equal a minus dq. And then you can see that a minus dq has the same form as the elements of your set, right? So a minus dq, if you want to expand, is a minus ax plus by times q, and that's equal to a times 1 minus xq minus byq. So the thing that is important to see is that it has the same form as ax plus by, right? And the only thing that you're not sure is that whether you know that this guy is positive, that r is positive, but it could be 0, and it has a form that you want for elements of the set. So essentially, what we can see now is that a would be a member of S if R is not 0. And we know that R is lower than D, since it's the remainder of the division. So R is not allowed to be in the set, because we said that D was the smallest number in the set. If R is smaller than the smallest number, then we got to a contradiction. So R cannot be a member of the set. So therefore, it has to be 0. Right? And that means that A is equal DQ. So the remainder of the division gave 0, which basically says that D is a divider of A. And we can do exactly the same thing, right, by symmetry, with B. So now we know that D divides both A and it divides also B. So D is a common divider of A and B. So the remaining thing we have to prove is that D is actually the greatest common divider. We know it's a common divider, but is it the greatest one? Is it the biggest one? So let's say, again by contradiction, let's say that we have a divider C, and we would prove that that divider has to be lower than D, lower or equal. So let's take C, which is a common divider of A and B. Therefore, A can be written as U times C, right? U is some term, and B is equal to V times C. V is another term that we don't really care about. We just care that U and C are integers. So now, based on that, we can write that D. We can use the fact that D equal AX plus BY. And we expand the definition of A and B, and we have D is equal UCXX plus VCY, which basically we can recognize that there's a common term C. So that shows that D is also multiple of C. Or alternatively that C divides D. And if C divides D, it means that C is lower or lesser or equal to D. So D is greater than any divider of A and C. D is greater than any common divider of A and B. Therefore, D is the greatest common divider. Right. So that's how we can prove the lemma before. So now how we apply this lemma? Again, it's going to be super simple once we have this lemma. We know that that P is a prime number. So by the fact that it's a prime number, nothing is going to be a divider of that number. And in other words, if you take any number A and you consider A and P together, the greatest common divider of these two is going to be 1. Because basically P has no divider besides 1 and itself. And A can have any number of divider, but the only thing that they're going to have in common is going to be 1. Except if A equal P, but that's not the case here. So if we apply the Bezout's lemma with A and P, when P is prime, we have the greatest common divider equal 1, and that gives us that there is x and a y, such as ax plus py is equal 1. And this is the same as saying that ax is equal to 1 modulo p. You just move the term yp to the other side, and any multiple of p is cancelled out modulo p. So therefore you have ax equal 1 modulo p, and that's saying that x is the inverse of a in p. So that proves that any element of fp prime has an inverse, which is x. So there you have it. We used very fundamental properties of algebra mostly about multiples and dividers and logic. And we were able to understand how RSA works, at least prove that it's consistent. Again, this is absolutely not a proof that RSA is in any way secure, because this is way beyond the scope of this series of videos. But I think that the result is quite interesting. We were able to reach a result that is non-trivial with a fairly small investment in mathematics algebra.